Welcome to our last annual, our last faculty seminar of the year. We started at the beginning of this year and we'll be continuing them next year. They're monthly seminars that the Center for Health Informatics and Bioinformatics puts out, so please watch out for our announcements. Today's seminar is by Dr. Lawrence Fu, and he's a research assistant professor at our department, and he has a PhD in biomedical informatics from Vanderbilt University. He's also the co-director of the evidence-based medicine information retrieval and Scientometrics lab here. He has published many articles, but, and I have to get this right, so I'm going to read this. He was the first one to publish the first paper that demonstrates the feasibility of predicting long-term citation counts for biomedical articles using only information available at the time of publication. So, welcome up here.
Okay, thank you, Anna. So thanks everybody for coming. So the main goal of my talk was to go through and discuss some of the basic citation metrics such as impact factor, citation count, because even though those are some of the most widely used metrics, they're still often used incorrectly or misinterpreted. So I just wanted to go through some of those basics and give people understanding so that they know how to use them and perform sort of fair comparisons when they're analyzing the literature. Now the first thing is, I'm going to start off with the definition of scientometrics because a lot of people haven't heard that term. Quote I found that I liked was that scientometrics is a field of science dealing with the quantitative aspects of people or groups of people, matter, and phenomena in science and the relationships. Now first off, scientometrics is a quantitative field. It's the quantitative evaluation of, when it says people or groups of people, that could be individual researchers, research groups, departments, universities, and even up to levels of entire countries. And when it says matter and phenomena in science, those are all sort of research products, outputs, articles, journals, and even these days, websites, or even people are sharing software, data sets. So it's not just confined to the actual scientific literature, and then also studying the relationships between all of these. Now, when I think of scientometrics, I sort of think of them in terms of sort of two general uses in which scientometric methods are used. One is the actual direct application in the conduct of research when people are performing their research work or clinicians are performing their duties in clinical care. So one of the uses is to help people find the highest quality articles in the literature, the best quality, the highest impact articles. And also related, helping libraries maintain their collections to help researchers and clinicians do their jobs. Now on the other side, you can think of scientometrics as being used sort of indirectly in the sort of supporting the conduct of research. Now, one obvious use is that either universities or departments can use scientometrics to evaluate and find who are the productive researchers or groups, and also use that for hiring and promotion, as well as determine how to efficiently use resources. And also, scientometrics has been used for national policy, determining how certain countries will focus their efforts, and also for governmental agencies in terms of using funding. Now, before I go into discussing individual metrics, I'm going to just discuss citation analysis in general, because all the metrics I'm going to be discussing, be it citation count for articles, impact factor for journals, or H-index, these are all based on measuring the quality based on the number of citations being received. So, and one other thing to note is that citations are not necessarily a positive indicator. I mean, that's what citation analysis assumes, but not all citations are positive. I mean, obviously there are times where something is cited because you're correcting something that someone else has done or improving on it. And in extreme cases, people are citing fraudulent research. Now, there's a couple sort of characteristics about citation behavior that are important that I don't think a lot of people realize, but you need to understand them if you were going to really use citation metrics correctly and not sort of apply them incorrectly. The first thing is that citations accumulate at different rates. There's no sort of standard behavior in terms of how citations accumulate. It's not as if a paper is cited a certain number every year after it's published. So if you look at this figure is graphing the way citations accumulate for a number of high-impact physics papers. So if you look at, say, the red triangle or the magenta asterisk, those you can sort of say have sort of long, broad, lasting impact. They're accumulating citations slowly over time. Now if you look at the green line, that has a high citation peak. So that received a lot of citations quickly and then sort of stopped receiving citations. Now there's also other kinds, such as if you look at the black circle, where Renner calls them sleeping beauties, where for a long period after they're published, they don't receive any citations. But then sort of maybe a related discovery happens on the side that increases the utility of the original publication, and that sets it off to start receiving a lot of citations. So as you can see that citations don't follow a certain pattern. And then if you look at, say, if you're just computing a single point, a citation count, you're basically compressing all of that into one time point. So it's important to realize that, and when you're calculating citation counts, that you sort of use a comparable time window and not using it to compare, say, a recent publication to a very old publication. Another important characteristic about citation behavior is that most articles don't receive many citations. If you look at this figure shows a sort of cumulative distribution of citations over all articles for a journal. So the first point on the bottom left shows that 50% of a journal's citations are received by the top 15% of highly cited articles. If you look at the second point, it shows that 90%, or almost all of the journal's citations, are received by only half of the journal articles. So what that tells you is that the bottom half of the citations are receiving very few, whereas most articles are receiving no citations or even just a couple. And this is more important for journal impact factor, which I'll talk about later. So this is another important thing to know, is that citation behavior varies tremendously when you look at different topics. So what this figure shows is the age of references cited in different fields and the average number of citations of these age. So if you look at molecular biology, the top line, it's above the mathematics line. What that means is that on average, molecular biology papers cite more references. Another thing to note is that the actual peak of mathematics is slightly over to the right. It's around 3 or 4, which means that on the average, mathematics cites older references. So together with that fact that molecular biology cites more articles and more recent articles, that means it's easier for papers in those fields to accumulate citations. So anytime you're using any citation-based metrics, you need to be aware of what the topic is or what the subject matter is, because if you're just comparing different metrics from different fields, the actual differences may not be a factor of the quality of the work, but just based on the field. So the last couple slides I've discussed is general characteristics about citation behavior, which highlighted some of the misleading aspects of citation metrics if you're not careful. And the most important thing I discussed was that some of the differences are not actually a result of the quality of the work. So one approach to minimize those effects is normalizing. So one of the important things is to normalize based on subject, if possible, or time, to make sure that you're doing a fair comparison. But also, it's not always easy to define a reference standard to perform normalization. Now, the first metric that I'm going to discuss specifically is journal impact factor. It is defined as the number of citations received in a given year to journal items published in the previous 2 years divided by the number of journal articles published in the previous 2 years. Now, the journal impact factor was designed as a method to compare journals independent of the fact that some of them publish more frequently or more articles. And you can think of it as the average number of citations received per article in a journal. And the one important thing to note is that the actual numerator counts citations to all published items, not just articles. So it's important because some journals may publish many editorials or letter to the editors or news items that receive citations. So that will increase their numerator without increasing the denominator. So that provides them a slight advantage. And one important thing about journal impact factor is that it should not be used to evaluate individual articles or as any type of substitute for citation count. The main reason is that because the distribution of citations over articles is very skewed, like I said earlier. So this shows the number of articles that receive a certain number of citations for 3 specific journals. So as you can see that it's heavily skewed to the left where most articles receive very few citations. This is a screenshot of the journal citation report at the ISI Web of Knowledge, which computes impact factor for most and all journals. This is showing the values for general internal medicine. As you can see, the journal citation report provides a number of other metrics to look at it. One of them is 5-year impact factor, which calculates it based on a 5-year window. So this number would be more useful if you're looking at, say, mathematics or another field, which has sort of a more durable literature. Okay, now, if you're looking at individual researchers and want to evaluate the impact and quality of their work, one possible approach is to take a simple, straightforward approach and calculate either totals or averages over their set of publications. Say the number of total citations that a researcher has received, or the average number of citations per publications. But the major problem with this is that this average you calculate could be dominated by a single publication. So it's hard to determine whether or not a researcher has had sort of long-lasting impact over a long period of time. As a result, H-index was developed to address this limitation. An H-index is defined as a scientist has an index H if he or she has H papers with at least H citations, and the remaining papers have less than H citations. So what this means is if someone has an H-index of 10, then they have 10 papers with at least 10 citations, and then all remaining papers have received less than 10 citations. Now this figures from the original Hirsch paper, and it provides a graphical representation of what the H-index actually is. So the decreasing slope represents a person's set of publications sorted according to how many times it's been cited. So the top left point is the paper that has received the most citations for that author. And the decreasing line is the decreasing number of citations as you look at the rest of their publications. And the point H is where this slope intersects the x equals y line. But one of the major limitations about H-index is that once a paper enters the H, what's called the H core, it doesn't matter how many more citations that those papers have received. So the problem is that if you have 2 scientists with H-index of 10, one person may have 10 publications with 10 citations, but the other one may have 10 publications with 100 citations each. H-index doesn't differentiate between those 2 and doesn't say there's any, doesn't let you know that there's any difference there. Now, in terms of evaluating groups of researchers, one approach could be another simple, straightforward approach, where if you're looking at, say, a department or a group, you would calculate the total number of publications or total number of citations or average number of citations that they've received. But the problem is when you're looking at larger groups of people, the actual variability between groups grows even more than if you're just comparing 2 people. So if you're trying to compare 2 individual researchers, they might work in different fields, or one person might be a younger researcher and another person's an older researcher. But if you're looking at a department, obviously those factors also apply, but then you have other factors such as one department is a much larger department, one may have more resources. So to compare either groups of researchers or even universities, you need to normalize the metrics to ensure that you're making more of a fair comparison. So one effort by the Center for Science and Technology Studies has been to normalize some of these basic citation metrics according to not only topic but also university size. So in this table here, the first column, P, is the number of publications produced by each of these universities. MCS is the mean citation score, which is the number of average citations received per publication. Now, MNCS is the mean normalized citation score. So what that means is they look at the average number of citations received per publication and divide that by the expected number of citations for all the fields that each of the university publishes in. Now, they determine the way to normalize this by looking at all of the journals that the publications are published in and determine what fields those are in. Those fields are based on the subject categories in the journal citation reports in the ISI website. And then they compute a weighted average based on what proportion of each publication is in each field. So if you say MIT publishes in, let's just say, 3 fields, and it looks at the average number of citations in each of those fields, then it would compute a weighted average for those 3 fields and then divide their mean citation score by that. So then for the MNCS, you can think of that or compare that to a value of 1 being an average impact for the fields that they publish in. So then obviously a higher number is a better score. Now you can see that this sort of result, if you look at it, it looks a lot different than a lot of typical rankings lists you'd see. Normally you would see Harvard to the top. But here you see a couple universities from Germany and Switzerland, which you may not think are necessarily should be up there. But according to these normalized impact measures, they are clearly having impact. So if you relied on more traditional metrics, say just publication count or citation, I mean, these clearly wouldn't be among the top because the German university has 4,000 publications. The Swiss university, the mean citation score is 8.9, which is significantly lower than the other ones. So as you can see, normalizing gives you another sort of way to look at the data that may not be as obvious as some of the more simpler metrics. So I'm just going to mention in passing that there are some other rankings lists for universities, but these are well known, but they're sort of based on manually generated sort of criteria, manually weighted. The academic ranking for world universities and Times Higher Education Supplement, they include things such as the number of Nobel Prizes that have been received by certain universities, a number of papers published in high-ranking journals like Nature and Science, and then they weight based on how important they think those are. So this is not really as principled approach as the previous one I discussed. Now, so far I've discussed a number of citation metrics and some of their limitations and how to use them. And now I'm going to discuss some of the sort of citation databases that provide this information. So if anybody wanted to perform their own analysis or play around with any of these to see what they can find, I'm going to go through 4 citation databases. Now, there's no one clear superior one. Each has their own sort of limitation. They don't all cover the exact same topics because of different agreements with publishers or different ways that they collect the data. Okay, so the first one is the Thomson ISI Web of Knowledge. It's the most popular one, the most well-known one. So this is one of their features called Citation Report. So anytime you do a search, if there's, say, a set of references or you're looking at an individual author. So this is an individual author that I looked at. It can sort of summarize a large body of articles with a number of metrics. So the top left figure shows the number of published items over a year for this author. It also shows the number of citations over a year. Now, if you look at the first article, the Genome-Wide Association study of 14,000 cases, that's the most highly cited article for this person. And it shows that it's been cited 2,982 times. So I'm just highlighting that because I'm going to go through and look at how many times cited is shown by each of the databases and show you that you can't really compare the two. And each database you have to sort of use independently. So the next one's Scopus, which is another well-known citation database. Here you can see that it says the paper has been cited 3,628 times. Now, the actual reason why these numbers varies, it's impossible to know. And there's no real sort of general rule you can take and say, Scopus is not necessarily always higher than ISI or the other way around. And Scopus also provides some other features, such as trying to summarize information about authors like this, where it highlights source history, such as the publications that the author is published in or the subject areas. One thing that I think Scopus does a little bit better is disambiguating authors. Because when I was looking at the authors for ISI, when you search for an author, what it's actually doing is looking in the author field and just matching that term. So most likely, I'm sure of the fact that when we were looking at the author's publications, those were not all from one person who was not the author of that top publication. But for this one, they automatically disambiguate based on the affiliations of the articles that they publish in. So another well-known option is Google Scholar. Google Scholar, the way they collect their set of information is through a combination of either automatic crawling or some agreements with publishers. Now their content is not as comprehensive as ISI and Scopus, because those products are corporate products with a lot more resources dedicated to it. And also I found Google Scholar, sometimes the data can be a little bit noisier in the sense that it includes preprints, presentations, and sometimes it shows different versions of the same publication as different publications. But it does have a nice feature where if you go in and log in, you can enable a profile and it'll automatically find all of your publications and then start recommending articles to you based on your previous publication history. And another one, which is probably the least known option for citation data, is Microsoft Academic Search. From personal experience, it has more errors than the other databases. It doesn't have as much coverage, but the one thing it does have is it provides an API to allow users to more easily consume the data or provide automated searches. So for ISI, it's possible where if you log in and do a search, you can manually download the records and it'll give you the text and you can parse out the fields and analyze the data that way. But for the other ones, it's very difficult. You'd either have to scrape the data or provide some other way. But with Microsoft Academic Search, you can actually use an API and perform automated queries to get the data and perform analysis that way if you would like. So now, to summarize for the metrics I've talked about so far, one thing is that there's no sort of single magic number you can use to just summarize large amounts of data. For example, when I showed the figure of citation rates or citations accumulating over time, if you're calculating a citation count at a certain time point, you're obviously losing all that information and sort of collapsing over that dimension. And if you are trying to compare either researchers or groups of researchers and you're expecting one number to provide some evaluation, it's just not going to provide you with the level of detail that you need. So the way, if you want to perform any analysis, what I would recommend is to use multiple metrics and sort of use those in combination and ensure that you're performing a fair comparison and not sort of comparing dissimilar things. Because a lot of times people, if they wanted to either compare a department, they'll just say, let's compute the average number of citations. But then you don't know if one has predominantly senior researchers, and then obviously it's easier for them to accumulate more citations. And obviously two of the major factors I've discussed are the time aspect and also the subject matter. You can't compare different subjects without any type of handling. Now you can either handle that up front in terms of pre-processing or restricting your analysis to a certain domain, or you can handle it the other way as normalizing, trying to remove that after the fact. Now, I'm going to sort of switch gears a little bit and sort of focus more on sort of newer directions in scientometrics and newer methods that have been developed. So with all the citation-based metrics that I've talked about so far, one of the major limitations is that we must wait months or years for all of these to accumulate. But everyone knows that these days, the way people are reading articles and journals is electronically. So it would seem that we should be able to measure impact and evaluate the quality much more efficiently instead of having to wait for like journal impact factors to be calculated every year. So one effort is what's called usage-based metrics, where people look at the number of times an article has been viewed, or number of times it's been downloaded. Now, studies have shown that the early number of web views can correlate with longer-term citation counts. But there's some considerations before we start using these more generally. Is that, first of all, a lot of the usage data is not standardized. So a web view on one website or one server is different or counted differently on another one. And also the actual value of what a web view indicates is not completely understood. Obviously, it's not the same as a citation in a regular peer-reviewed journal publication. Now here I show PLOS One website as an example of usage-based metric. So here this is sort of the detail page for a certain article where it shows the HTML page views, PDF downloads, XML downloads over time. So I like this display because it gives you the information in graphical format and it lets you make your own interpretations. It doesn't try to just give you one number and say, these are the number of times it's been viewed. Another thing that this website shows is it compiles a lot of the citations from either Scopus, ISI Web of Science, and other databases, as well as showing citations in other sort of social media, social network sites, such as Site You Like, which is a reference manager, or Mendeley, and other sort of social media sites, as well as compiling blog citations and having sort of a comment section. So obviously, we don't know the value of trying to count how many times it's been referenced in a social media website, but there may be some value, and they provide this information to users, so let them use it as they will. Now, another piece of work, this is some of the work I've done on predicting citation count, and this is another effort to try to overcome the limitation of waiting for citations to accumulate over months and years. And this work was investigating whether it was feasible to predict long-term citation count using information only available at the time of publication. And the information that it used was either content information or scientometric information. And the content features were the title, the abstract, and the mesh terms from the PubMed record of an article, and combining those with scientometric features such as the number of citations received by the first and last authors, the journal impact factor, or the quality of the publishing of the author's institutions. So once I built these training corpora, converted them into a format suitable for machine learning models, trained the models on the corpus, evaluate their performance, and determine whether or not they were overfitted. So this slide summarizes the results. The first figure shows that it was in fact possible to predict long-term impact using information only available at the time of publication. What the figure shows is that when you look at 4 different thresholds, because I predicted whether or not an article would receive more than 20 citations, or more than 50, or more than 100, or more than 500, is that the prediction performance was very high. For 500 citation threshold, the AUC value was 0.92. The second figure shows that the models were able to work well on articles that were not used at all during the training. And the third figure shows that when you look at the actual features, either the content features or the scientometric features, that both of those features are important to reach optimal performance. And also 4 is when you look at actual features, some of the most important features were the first author citation count, the journal impact factor. So finally, I just wanted to sort of make a comment, because in the beginning I was discussing some of the sort of more traditional citation-based metrics. And as we all know, that the sort of way research has been done, is being done and sort of communicated has changed drastically recently, with the internet, in terms of not only how knowledge is being communicated, but also what is being shared. So when you think of software and data, those types of things. So there's a large movement towards being more open and having more open science and more open access. Part of that is due to the increase in retractions as shown by this figure. So there's a push for researchers being able to reproduce other work. and for fraud detection, also just to increase not only the efficiency but actual quality of work. So as part of that, developing new methods and new metrics to evaluate those, because if someone's creating a new data set or a new software package that is being used by many people, that is definitely another instance of impact that we need to measure. So future methods will hopefully capture that also. So the rest was, and thank you, and I'll take any questions you may have.
I just wanted to ask about, I'm from the Department of Child and Adolescent Psychiatry, and we track our researchers both in terms of current publications and then starting to look at the different impact factors as a metric that's evaluated. And one of the things that comes up regularly is valuing different kinds of publications. And I wonder if you could talk at all about how to factor in first and last author versus, just a name in a long list, the relative number of authors on a given publication. Are there elements of that are included in any of these indices?
Well, there's a lot of variations of these, either impact factor or citation count, where people look at that, where they have fractional counting. So if there's a long list of people, some people would take the citation count and divide it by the number of authors. So there are certain ways to factor that in, or add more weight to being a first author or a last author.
Do you have any opinions about the best way to do that?
I mean, I don't really have an opinion. I mean, I understand the reason to try to incorporate that information, but I haven't really looked into it closely enough to see.
If I can contribute the thought to this question, I think that in the era of highly collaborative and complex science, I think it's very detrimental to the efforts to convince people to work together productively and sharing their ideas and being open and team players. If someone starts dividing up, the theoretical contribution without knowing necessarily what's the benefit of it. On the other hand, we're definitely losing time to create this teamwork. So I think that's not a very, very good idea in that sense.
Just commenting on the same thing. In different fields, positions count differently. So in the biomedical, the last author is often the most important. In many other fields,
right.
In nursing, for example, it starts at the left and becomes more important. The last one is the least important.
Well, so that's definitely another point to support not comparing between different topics, but another reason. Right, exactly.
I was curious about, you were saying how the 4 different citation databases, Web of Science and so forth, that there were differences between them. I couldn't quite tell the data because of the last one, but it looked like the others were off by maybe 10 or 20%.
Oh, the actual number of citations?
Have you done any sort of looking systematically across articles? What's the average sort of percentage difference between the citation counts in these different?
Well, I mean, that's what I was trying to say, is that you can't say generally like this percentage higher all the time. Is that what you're saying?
Yeah, not that it's higher or lower, but it just looked like the first 3 were in the ballpark, and it looked like the fourth one was really I mean.
Was it like 1,400? It was lower?
Yeah, it was like a factor of 3 difference
right.
As opposed to maybe 20%, 10-20%. So is that? I mean, it's just completely all over the map as far as the differences between the 4.
I mean,
is that one always sort of a big outlier?
Oh, the Microsoft's.
Yeah.
Well, that one I think is a big outlier because Microsoft hasn't really dedicated that many resources to it. Yeah. I've actually seen. I mean, I've seen significantly more errors in it, such as sometimes the first author is just missing and the second author is listed as the first author, or I've seen just incorrect journals for certain articles, things like that.
Wow. Okay.
So yeah.
I just wanted to add to that. So Jeff Bundy and I have been looking at multiple different sources, and Jeff did he checked out a number of papers and a number of different databases, and it is random. Whereas Google was very dirty because they also included things like newspapers and things like that, and that was considered a citation. But over the years, it seems like some like Swiftis and Thompson have gotten a little bit closer together, but they have different data, they don't count all the same journals, and so and they've tried to exclude the news but
I don't think they
know
do.
what they're, that they do at all. But it was hard to generalize, like to say that this one will always be about 20% higher than that one, or, you know, it seemed like it was by field, many, and how popular the article was in other fields that you may not have expected it to get cited in. So.
I haven't really done any systematic study of this, but one thing that I have noticed is that Scopus tends to include more non-English language journals than ISI does, but then that doesn't mean that the Scopus count is always higher. There are all kinds of different discrepancies. And you know, there's no real clear way of saying which one is better because it's mostly pretty much random.
Do any of them exclude self-citations?
For some of them, they'll have another option for removing self-citations.
I had a recent article, and after that I received an email asking me whether I would agree of having this article placed in some arm of an investigation into reproducibility. So I just wondered what criteria they use to choose, or is it totally a random process to choose articles that apparently, if they have funding, they will try to actually replicate our experiments.
So you're saying you were contacted because it was some group they wanted to reproduce? I don't think there's some sort of centralized effort where someone's determining that, you know, there's certain ones that should be, you know, reproduced or not. I mean, my comment was just.
Was it a group of scientists or was it a group of biblio?
I don't remember the name of the organization, but they have a website and their goal is to validate articles because of the problem that you mentioned.
Because there were a couple studies that were done that they were trying to validate articles. Some journals were doing it, and there were organizations that were doing it. I don't know whether there's but it would be interesting if there's an ongoing effort to try to validate the literature specifically.
Apparently, and they were emphasizing if money becomes available, as if they're trying to get funding.
Well, yeah, my comment was just in general that I've noticed this trend where I'm not really familiar with any specific efforts or any websites or bodies trying to do that.
Because some journals were trying to verify microarray, papers that were based on microarrays, and found that 1 in 20 of the papers could be validated based on the amount of, data, validated based on the amount of data that was publicly available in the databases. So it was, there's been a lot of interest in that.
So the slide that you showed from this Swedish organization that normalizes metrics, I think that there is a very, very important observation in that slide, and then also in the remainder of the list that's not shown here. Okay. Specifically, the normalized average number of citations per paper is ridiculously small.
You talking about? You're saying very difference from one?
I'm saying that the number of citations that are receiving is very, very, very small on average. And third, that's one observation. And this is the cream of the crop, supposedly, you know, at least in a relative sense. But what's even more remarkable is that if you go to the 100 position in that list, the difference of the 100 or the 300 or the 500 institution to the top is basically, you know, half a unit or some other extremely small number, which is another manifestation of the fact that the number of citations received, the majority of the literature, is extremely small. There's only a very small number of papers that really are highly cited. So I was wondering if you have any insight about whether this is a reflection of the fact that the majority of papers are worthless, or the fact that there's not enough attention to be paid to each and every paper, although there might be intrinsic work in there, and this manifests in low citation numbers, although the merits of the paper may be there and undiscovered yet, or maybe they're discovered in some other paper and so forth and so on. So do you have any insight about this phenomenon?
So you're curious if just the total number of citations, or you're just saying that for the lower
The vast majority that they're receiving so few citations, excuse me.
Right.
So do you have an insight about they're truly, you know,
Are they truly worthless, or is
worthless,
they just not?
or is there something there and somehow it cannot possibly be translated to high citation numbers because of the scarcity of citations overall? You cannot have an infinity of citations. It's a reflection of how many people are writing papers that are citing.
Right. Well, I mean, there's actually sort of a discussion about the philosophy of citations, because the actual process of citing something, it's sort of a social process. You're not really, citing based on just quality. So a lot of times people, they'll cite things that they are already previously highly cited. So, obviously the most prominent researchers from high-profile labs who've already done good work, their papers are going to be read more often anyways, and then there's already some sort of halo effect, so they will, automatically receive a lot of citations. So for these other institutions which maybe are not as prominent, their work may be good, but they're just not going to be read or cited. So that might, I don't know if that addresses.
It seems like you wanted to evaluate that, you'd have to maybe look at the number of average citations per paper over time, because the amount of literature has increased. So if that number has decreased, the average citations over time, it's going to give more weight to the idea that it's a reflection of just there's more and more literature, and it's less likely that people can pay attention to that.
But still, yeah, you're right. However, it's still constrained by the total number of citations, which over time is larger, but still it's very finite relative to the space of publications. Are there any studies of substitution effects? Let's say I publish 10 papers, okay, and 9 of them get 0 citations, and 1 of them gets, say, 1,000 citations. And this one that was cited contains elements from all these other different papers that were not cited very much. Are there any studies of substitution effects for content?
No, I'm not aware of any studies that look at that.
I think there would be. I mean, I feel like there's a lot of work that leads up to some grand work where you have a lot of papers that are just sort of preliminary work, sort of interesting and seems to be going down a direction. At some point, your work reaches a point that it becomes consumable by a mass audience, and that's the work that everybody cites. And you provide it in your work to sort of show people that you're moving along in something, and maybe try to gather some consensus. But until you publish that definitive paper,
so there's a consolidation, concentration of ideas and results, and at the point of higher concentration, you get a lot of citations. You're saying?
Yeah.
And the previous work was absolutely necessary in order to reach that point and worthy of publication and getting credit for in some way.
Right. But I don't think it's necessarily cited. I mean, I imagine there's a lot of work like that. Because I think a lot of stuff ends up in dead ends too, where you do a bunch of preliminary stuff and then you can't replicate it in a larger study, you can't replicate it in a larger group, and then it just doesn't get cited. So I think a lot of work is worthless, but it's worthwhile because it showed you either pertinent negatives or
close
things.
the door.
Yeah, or close the door on an avenue of thinking that may have continued on, or that somebody could have come up with and didn't realize that it was a dead end.
Any other questions? Yeah.
So I would be interested. I think a lot of people talk about these different databases and looking at the different citations and realizing that they're all different and they're all over the place. And I'd be more interested in knowing the relative differences between articles in one database. And so so you just take one database. Like if you have this chart, for example, and you took one of the databases, could you replicate this one chart, even with all the errors and all the things in each one? Because the errors are systematic and things are more important in general get cited more often. Do you know if anybody is working down that avenue of just really looking at one database and trying to have some baseline measure for that, for what a citation is in that one database, and then looking at the relative differences?
What do you mean by relative differences?
So the genome study that you saw, if you compare that to all the other GWAS studies in each database, do you think that would always appear in the same place, in the same rank?
Okay. Well, I haven't seen any studies that do that. I mean, a lot of studies I've seen where they'll sort of focus on either a certain topic and then look at each of the citation databases and see how they differ for that. So they'll make some sort of general conclusion saying for this topic or this area, these sets of papers, this database is better for this. But then it's hard to sort of generalize for other uses.
So the rankings can be radically different between each.
I'll bet that when we used to look at all the nature journals and didn't you look at them with Scopus and with Thompson at one point? Because
I did.
I thought that the papers that got a lot of citations tended to be at the top in all of them. And then it was when you had fewer citations that the order bounces around.
I don't think we actually compared the ranking. I do know that
I think that's the impression I got.
Scopus usually got slightly higher citation counts for the nature journals than ISI did. But
the individual papers, you don't remember?
I don't think we looked at that.
N is always so small when you're looking at individual papers.
The other thing was that the calculations that ISI uses to do the impact factor are not quite the same as the kind that you can actually do yourself using their website. They and usually the number of citations that gets counted for the impact factor is a little bit higher than what you can actually find because
they don't use one.
They
don't use their own data.
Well, it's because they only look at the journal title. They don't try to identify the individual article. So if the citation is malformed, it'll get counted in the impact factor, but not in anything else that you can do.
But do you think if you calculate those impact factors on one database, it would all have the same ranking? So for England, the New England Journal would always be #1, no matter what database you use.
At the journal level, most likely.
Yeah.
As you get down into the more granular level, it would probably start to get noisier.
Okay. Oh, wow.
Yeah, so you mentioned that one of the applications of these kinds of metrics were for researchers to explore the literature. Are you concerned that it might be kind of a self-fulfilling prophecy? So I mean, if you have certain papers at the time of publication that have high predicted citation counts, they get bumped to the top of the search engine results.
Right.
More people read them.
You're talking about predicting citation count, those models?
Mm-hmm.
Well, I mean, if those models were used in sort of a real world application, they would have to be sort of retrained regularly over time to sort of account for that. So I mean, it wouldn't be, obviously if you train the models on a period a while ago, and then sort of use them for a while, that would in fact change the actual citing behavior over time.
Yeah.
So, yeah. Any other questions? Okay, thank you.